atmospheric escape is the loss of planetary atmospheric gases to outer space. Thermal escape mechanisms. One classical thermal escape mechanism is Jeans escape. In a quantity of gas, the average velocity of a molecule is determined by temperature, but the velocity of individual molecules changes as they collide with one another, gaining and losing kinetic energy. The variation in kinetic energy among the molecules is described by the Maxwell distribution. The kinetic energy and mass of a molecule determine its velocity by. Individual molecules in the high tail of the distribution may reach escape velocity, at a level in the atmosphere where the mean free path is comparable to the scale height, and leave the atmosphere. The more massive the molecule of a gas is, the lower the average velocity of molecules of that gas at a given temperature, and the less likely it is that any of them reach escape velocity. This is why hydrogen escapes from an atmosphere more easily than does carbon dioxide. Also, if the planet has a higher mass, the escape velocity is greater, and fewer particles will escape. This is why the gas giant planets still retain significant amounts of hydrogen and helium, which have largely escaped from Earth's atmosphere. The distance a planet orbits from a star also plays a part. A close planet has a hotter atmosphere, with a range of velocities shifted into the higher end of the distribution, hence, a greater likelihood of escape. A distant body has a cooler atmosphere, with a range of lower velocities, and less chance of escape. This helps Titan, which is small compared to Earth but further from the Sun, retain its atmosphere. An atmosphere with a high enough pressure and temperature can undergo a different escape mechanism, hydrodynamic escape. In this situation the atmosphere simply flows off like a wind into space, due to pressure gradients initiated by thermal energy deposition. Here it is possible to lose heavier molecules that would not normally be lost. Hydrodynamic escape has been observed for exoplanets close to their host star, including several hot Jupiters and a hot Neptune. Significance of solar winds. The relative importance of each loss process is a function of planet mass, its atmosphere composition, and its distance from its sun. A common erroneous belief is that the primary non-thermal escape mechanism is atmospheric stripping by a solar wind in the absence of a magnetosphere. Excess kinetic energy from solar winds can impart sufficient energy to the atmospheric particles to allow them to reach escape velocity, causing atmospheric escape. The solar wind, composed of ions, is deflected by magnetic fields because the charged particles within the wind flow along magnetic field lines. The presence of a magnetic field thus deflects solar winds, preventing the loss of atmosphere. On Earth, for instance, the interaction between the solar wind and Earth's magnetic field deflects the solar wind about the planet, with near total deflection at a distance of 10 Earth radii. This region of deflection is called a bow shock. Depending on planet size and atmospheric composition, however, a lack of magnetic field does not determine the fate of a planet's atmosphere. Venus, for instance, has no powerful magnetic field. Its close proximity to the Sun also increases the speed and number of particles, and would presumably cause the atmosphere to be stripped almost entirely, much like that of Mars. Despite this, the atmosphere of Venus is 2 orders of magnitudes denser than Earth's. Recent models indicate that stripping by solar wind accounts for less than 1/3 of total non-thermal loss processes. While Venus and Mars have no magnetosphere to protect the atmosphere from solar winds, photoionizing radiation and the interaction of the solar wind with the atmosphere of the planets causes ionization of the uppermost part of the atmosphere. This ionized region in turn induces magnetic moments that deflect solar winds much like a magnetic field. This limits solar wind effects to the uppermost part of the atmosphere, roughly 1.2–1.5 planetary radii away from the planet, or an order of magnitude closer to the surface than Earth's magnetic field creates. Beyond this region, called a bow shock, the solar wind is slowed to subsonic velocities. Nearer to the surface, solar wind dynamic pressure reaches a balance with the pressure from the ionosphere, in a region called the ionopause. This interaction typically prevents solar wind stripping from being the dominant loss process of the atmosphere. Comparison of non-thermal loss processes based on planet and particle mass. The dominant non-thermal loss processes depends on the planetary body. The relative significance of each process depends on planetary mass, atmospheric composition, and distance from the Sun. The dominant non-thermal loss processes for Venus and Mars, two terrestrial planets neither with magnetic fields, are dissimilar. The dominant non-thermal loss process on Mars is from solar winds, as the atmosphere is not dense enough to shield itself from the winds during peak solar activity. Venus is somewhat shielded from solar winds because of its denser atmosphere, and as a result, solar pickup is not its dominant non-thermal loss process. Smaller bodies without magnetic fields are more likely to suffer from solar winds, as the planet is too small to have sufficient gravity to produce a dense enough atmosphere and stop solar wind pickup. The dominant loss process for Venus' atmosphere is through electric force field acceleration. As electrons are less massive than other particles, they are more likely to escape from the top of Venus's ionosphere. As a result, a minor net positive charge develops. That net positive charge, in turn, creates an electric field that can accelerate other positive charges out of the atmosphere. As a result, H+ ions are accelerated beyond escape velocity. Other important loss processes on Venus are photochemical reactions driven by Venus's proximity to the Sun. Photochemical reactions rely on the splitting of molecules into constituent atoms, often with a significant portion of the kinetic energy carried off in the less massive particle with sufficiently high kinetic energy to escape. Oxygen, relative to hydrogen, is not of sufficiently low mass to escape through this mechanism. Phenomena of non-thermal loss processes on moons with atmospheres. Several natural satellites in the Solar System have atmospheres and are subject to atmospheric loss processes. They typically have no magnetic fields of their own, but orbit planets with powerful magnetic fields. Many of these moons lie within the magnetic fields generated by the planets and are less likely to undergo sputtering and pickup. The shape of the bow shock, however, allows for some moons, such as Titan, to pass through the bow shock when their orbits take them between the Sun and their primary. Titan spends roughly half of its transit time outside of the bow shock and being subjected to unimpeded solar winds. The kinetic energy gained from pickup and sputtering associated with the solar winds increases thermal escape throughout the transit of Titan, causing neutral hydrogen to escape. The escaped hydrogen maintains an orbit following in the wake of Titan, creating a neutral hydrogen torus around Saturn. Io, in its transit around Jupiter, encounters a plasma cloud. Interaction with a plasma cloud induces sputtering, kicking off sodium particles. The interaction produces a stationary banana-shaped charged sodium cloud along a part of the orbit of Io. Impact erosion. The impact of a large meteoroid can lead to the loss of atmosphere. If a collision is energetic enough, it is possible for ejecta, including atmospheric molecules, to reach escape velocity. Just one impact such as the Chicxulub event does not lead to a significant loss, but the terrestrial planets went through enough impacts when they were forming for this to matter. Sequestration. Sequestration is not a form of escape from the planet, but a loss of the molecules from the atmosphere and into the planet. It occurs on Earth when water vapor condenses to form rain or glacial ice. It also occurs on Earth when carbon dioxide is sequestered in sediments, or cycled through the oceans. The dry ice caps on Mars are also an example of sequestration. One mechanism for sequestration is chemical. For example, most of the carbon dioxide of the Earth's original atmosphere has been chemically sequestered into carbonate rock. Very likely a similar process has occurred on Mars. Oxygen can be sequestered by oxidation of rocks. For example, by increasing the oxidation states of ferric rocks from Fe2+ to Fe3+. Gases can also be sequestered by adsorption, where fine particles in the regolith capture gas which adheres to the surface particles. Dominant atmospheric escape and loss processes on Earth. Earth is too large to lose a significant proportion of its atmosphere through Jeans escape. The current rate of loss is about 3 kilograms of hydrogen and 50 grams of helium per second. The exosphere is the high-altitude region where atmospheric density is sparse and Jeans escape occurs. Jeans escape calculations assuming an exosphere temperature of 1800 kelvins show that to deplete O+ ions by a factor of E would take nearly a billion years. 1800 K is higher than the actual observed exosphere temperature. At the actual average exosphere temperature, depletion of O+ ions would not occur even over a trillion years. Furthermore, most oxygen on Earth is bound as O2, which is too massive to escape Earth by Jeans escape. Earth's magnetic field protects it from solar winds and prevents escape of ions, except near the magnetic poles where charged particles stream towards the Earth along magnetic field lines. The gravitational attraction of Earth's mass prevents other non-thermal loss processes from appreciably depleting the atmosphere. Yet Earth's atmosphere is 2 orders of magnitude less dense than that of Venus at the surface. Because of the temperature regime of Earth, CO2 and H2O are sequestered in the hydrosphere and lithosphere. H2O vapor is sequestered as liquid H2O in oceans, greatly decreasing the atmospheric density. With liquid water running over the surface of Earth, CO2 can be drawn down from the atmosphere and sequestered in sedimentary rocks. Some estimates indicate that nearly all carbon on Earth is contained in sedimentary rocks, with the atmospheric portion being approximately 1/250,000 of Earth's CO2 reservoir. If both of the reservoirs were released to the atmosphere, Earth's atmosphere would be even denser than Venus's atmosphere. Therefore, the dominant loss mechanism of Earth's atmosphere is not escape to space, but sequestration. References. Further reading, Hunton, D.M. Atmospheric Evolution of the Terrestrial Planets. Science 259, 915 920. Bibcode, 1993 Sci. 259 915 H. doi, 10.1126/Science. 259.50 97.915. Lammer, H. Bauer, S.J. Atmospheric mass loss from Titan by sputtering. Planetary and Space Science 41, 657 663. Bibcode, 1993 P&SS. 41657 L. doi, 10.1016/0032-0633, 93, 90049-8. Zahn, Kevin J. Catling, David C. Our Planet's Leaky Atmosphere. Scientific American. Learning materials related to atmospheric retention at Wike University.